Hello everyone, here's a Physics 30 example from Unit 5, Atomic Theory, and this is the charge to mass ratio of the electron, or properties of the electron. So first example here, we're given a charge to mass ratio of an unknown particle. All we're told is the value for the charge to mass ratio and that the particle has 4 electrons in excess. So let's go ahead and start writing out what we know about this situation. We know the charge to mass, and that is 7.83 times 10 to the 10 coulombs per kilogram. Okay, we know that the charge is going to be 4e, so we can substitute that in, and we're trying to get the mass, aren't we? So we can just substitute this in for Q, and we should then be able to solve for mass. Pretty simple. So let's go ahead. We'll go mass is equal to the charge Q, so this would be Q over the charge to mass, and so that means that the charge is going to be 4e. So the mass is 4e over the charge to mass ratio, which is 7.83 times 10 to the 10 coulombs per kilogram. And so we can go ahead and just plug that into our calculator. What we would do is go 4 times the elementary charge over this value. And that's going to give us a mass of 8.17 times 10 to the negative 30. And of course, that's going to be in kilograms. We can just double check that we've, oops, I forgot the G. Of course, the coulombs cancel. This kilogram is going to come up to the top to give us the kilograms. And there we have it. And for the second example, we have a parallel plate system. So we've got a voltage applied across a gap. This side is going to be positive. We can tell that by the orientation of the battery sign. So this is going to be positive. And this side is going to be negative. Let me just get my red pen. There we go. This is going to be negative. Although we're only asked to find the charge to mass ratio, so the charge of this particle is irrelevant. It just helps us to sort of paint a picture. Okay, so the particle, whatever it is, starts from rest. We're going to assume that it's right next to this plate right here. And before the voltage is applied, it's quite happy to sit there doing nothing. Once the voltage is applied, what we're seeing is that it's then accelerated through the uniform electric field, and it leaves with a final velocity here. So as it moves through this field, it's going to gain energy. The potential electric energy is going to be completely converted all the way to kinetic energy. So in other words, at this point here, it has 0 kinetic energy, but it's going to have its maximum potential electric energy. At the end of its, at the edge of the electric field, it's obviously used up, or it's going to be at its lowest electric potential energy of 0, but it's now gained all this kinetic energy. So we're going to write a statement with regards to the energies. We're going to say that the total energy initial has to equal the total energy final. We've seen this before, haven't we? And so what's the total energy initial? Well, let's go ahead and put all of the possible energies in. I'm going to say there's electrical energy and there's kinetic energy. These are both initial. And then afterwards, there's going to be electrical energy and kinetic energy. Final. But as we've mentioned, the lowest energy state for this is, in terms of electricity, is going to be right here. It's going to have an energy state of 0. In fact, if you use the analogy with the gravitational potential energy, we can essentially call this the ground. And if you were to turn your head 90 degrees to the left, 90 degrees counterclockwise, you can treat this to be the 0 height that you would drop a ball from. And this would be the maximum height you drop the ball from. So if this was a ball and you had the ball here, it's got its maximum potential energy at the top, and then at the bottom it will have 0 potential energy. So in physics 20, when we drop the ball, we talk about this potential energy converting to kinetic energy completely. And that's exactly what's going to happen here. So we can say that at the beginning, there is no kinetic energy, And at the end, there is no electrical energy. So we're left with a statement that says the electrical energy, the potential electrical energy, is going to be equal to the kinetic energy. Okay, and that's going to be the final, and that's going to be the initial. So what do we know about both of these? Well, hopefully we've got this etched into our memories by now. This is half mv squared, and the potential electrical energy is VQ. So what are we trying to do? We're trying to find the charge to mass ratio. Well, take a look. There's charge, there's mass. So now all we have to do is rearrange this and solve for Q over M. So we're going to go ahead, we'll go Q is equal to V squared, and we'll go over 2, because we've got the half. The M is going to be divided over here, so that's M, and then this is V. So our charge to mass ratio, which we're asked to do in the question, is the speed, which is 2.9 times 10 to the 6 meters per second, that's squared, don't forget to square, divided by 2 times the voltage, which is 1200 volts. And that's going to give us a value 3.50 times 10 to the 9, and it's charge to mass, which is coulombs to kilograms.